peaks here, 45 degrees over this way, it'll drop off by about half, and 45 degrees this way, drop off by about half. This antenna, now to get another 3 dB, we got to double the number of elements again. 1, 2, 3, 4, assuming this one's here. So this antenna has a theoretical gain of around 6 dB, which means that the beam width is going to be more like about 20 degrees this way, 20, 25 degrees this way, and 20, 25 degrees this way. Not real good, but still good enough for the purposes we're interested in. To be really effective on getting a really tight beam width on your rockets or balloons, what have you, we need a boom that's a lot longer than this. We need to get the beam width down very narrow. All right, so enough about this antenna. This is for the 440 band. There's different ways of matching antennas. This one is cut for the 2 meter amateur band, 144 to 148 megahertz. And again, this is homemade out of a piece of 1x2 and some scaffolding and tubing and some wood screws put in here to hold the elements in place. Now these kind of antennas I don't mount outdoors. These are strictly ones I carry around with me for balloon type events, although I don't carry this one anymore because I've got a much bigger one that I carry. And this one you can see with only a total of 5 elements is not going to be real directional. But it still gets you in the ballpark. And you can track and you can tell if you're tracking a balloon that's up here at altitude, you can definitely tell the signal strength drops off as you move this. All right, so matching into the antenna. Typically, as hams, we use 50 ohm coaxial cable. And this is actually something called mini RG8 miniature. So it doesn't have quite as good a qualities as the RG8 cable, but it's a little easier to handle. And the impedance coming out of this cable is 50 ohms. And the impedance of this element is something we've got to match this 50 ohms to. So this type of match here is called a delta match. And what we do, notice I've got a loop of cable here. This loop of cable is cut to a specific length. And it's soldered up here a certain way. And you can look in the AWRL handbook to see how to do this. They also have an antenna book as well. You can come up and look at this later. This little loop of coax soldered in here in a specific way makes a diode. And it also does an impedance transformation. So we're coming from 50 ohm coaxial cable, which is not a balanced line, it's an unbalanced line. And by use of this piece of cable, the same type of material to a specific length based on the velocity factor of the cable, we're able to transform this 50 ohms unbalanced impedance into something closer to 200 ohms balanced. And then you have to play around with the adjustment of the distance here. And you can do that with some kind of a directional RF power meter. You can use it with a field strength meter. There's a variety of ways to adjust this to get these optimized. And even if you don't have them perfect, as long as they're fairly close, this kind of antenna will work okay. And again, it will not perform as well as an extremely well-designed Martian antenna, but it'll perform fairly close and not cost you a lot of money to build. Here's one that has a, what we call a gamma match. So you can't really tell much about it, but I've got a coaxial connector here, and the ground side of the coaxial connector is actually grounded to the center of this driven element here. And a length of wire, and then there's a variable trimmer capacitor here. And so by adjusting this trimmer capacitor, we can again match the impedance to this antenna. So there's a lot of factors that play into it. The particular point where this is along here has some effect on the impedance that we're trying to match to. And we can compensate by adjusting this capacitor. Again, if you look in the handbook, you can can get ideas on approximately the right lengths to set this and approximately the right size of capacitor to do this, to do the matching. And this particular one was made out of some scrap lumber, and these are welding rods, and they weren't quite long enough, so I extended them by soldering some wire on the end. And this has worked reasonably well. I used this one to track a Russian satellite a few years ago, and I actually built it specifically for that purpose. Here's another Yagi antenna. Again, it uses the, maybe you can kind of see this Z element, or driven element. This one is cut for the 900 megahertz band, and I built this specifically for ballooning. Again, I would not leave this outside, and you can see this one's kind of bent up. It's just been thrown around my workshop. Before I would use it, I would take time to straighten the elements out and get them centered real well. And then let me talk about one last antenna, and then I'll be done. By the way, I did a few years ago build two different antennas on these wooden booms and varnished them and put them up on a tower out here in this West Texas weather. And trust me, they don't last too long in this West Texas sun and rain and wind. They're good for about a year before they begin to fall apart. This is a directional antenna. This is called a loop antenna. And this is for a much lower frequency. This is actually for the 10 meter amateur band, 28 megahertz. And on a lot of the balloons, and also on the rocket last year, we flew a 28 megahertz beacon. One of the reasons we like to fly the 28 megahertz beacon is because when the payload is laying on the ground, the 28 megahertz couples into the ground very well. And you can actually hear that out to about 5 miles with a mobile set up with a non-directional antenna. And so if you're close enough to hear the ground wave signal on the 10 meter beacon at 28 megahertz, then you can get out your more directional antennas to track down the VHF beacon on 2 meters or 40 megahertz or 900. So this one is, again, you can go to the AWL handbook and you can find the specific dimensions to cut these loops. I built this specifically for that rocket flight last spring over in Las Cruces. And you can see maybe there's some capacitors here, there's a little trimmer capacitor. This loop is actually resonated at the frequency of interest. And I have actually forgotten, and didn't get a chance to look it up today, but the way this works is it's got a null. When you turn this, let's say in the antenna, the signal source is over there. When you turn it this way versus this way, one of those ways gives you a null on the pattern, and I don't remember off the top of my head which way it is. The length of the cable has to do with the velocity factor and some other things. The velocity of radio signals through cable is different than free space. And typically in a cable it's about 70% or 68% or 74% depending on the top cable. And so again, you get all the dimensions for this. This works reasonably well. It's not quite as impressive as a really good antenna of this type. And usually when I go on these balloon flights, I have a whole bunch of stuff strapped on the roof of my Jeep, including a 30-foot telescoping tower. And I've got this really long 2 meter Yagi that sometimes I'll put on the telescoping tower and run up if the balloon payload's down and we really don't know where it is. And sometimes that's beneficial. Anyway, it makes quite a rig, especially when you're driving a few hundred miles to some launch. Makes a lot of noise in the wind as you're driving down the highway at 70 miles an hour. All right, any quick questions? All I'm trying to do is give you an overview of what you do. Yes?
On the last antenna, the shielding of the wire doesn't affect it, or doesn't hamper it?
It's, if you come up and look at this later, you'll see that the way this is hooked up, it actually does not make a complete loop on the shield. And again, if you look at that overall handbook, they'll give you a little bit more discussion on the technical side of that. Wasn't really prepared to talk about that too much tonight. I just trying to quick up